Number 8 wants you to calculate the magnetic flux in this triangle here. And the triangle looks like this. It's sort of a triangle like this. There's a 60-degree angle here. This is a 1 Tesla magnetic field out here. And the triangle has a 20-centimeter side. So if you look at it carefully, the problem has been oriented so that only half of the triangle has any magnetic field flowing through it at all. And so what we really need here is then the area of this half a triangle here. Why the area? Because magnetic flux, which is what you're being asked for here, is the magnetic field strength times the area. Now normally there's a cosine theta in here, but you can see that the normal to the area is straight up out of the page, and the magnetic field is straight down. So there's either a cosine of 0 or 180 in there, which is going to be 1 or -1, but we're just interested in the magnitude of the flux, so we won't even worry too much about the sign of the flux, but technically it would be a negative because the area is up and the magnetic field is down. So you need the area. How much of this area is being inundated with a magnetic field? And it's half the area of this triangle right here. So if you look at the area of this triangle here, the area here is definitely 1/2. The base of this triangle here is going to be the 0.1 meters. There's a 1/2 base, and then the height of it right here, I believe if you calculate, it's going to be 0.2 times the sine of 60. Just a little trigonometry in there. If you know this hypotenuse, this angle, that side there is related to the angle via the sine function, which we all know and love and stuff. So there'd be your area right there. Now, if you wanted to get the total flux in, you would just multiply the two. In other words, the magnetic flux would be this quantity right here, as I mentioned here, the area, which comes directly from this equation. You can put it in your calculator and figure out what it is, times the 1 Tesla. That will give you the answer to the magnetic flux in there. I got something like 8.86 times 10 to the -4, and the units of flux are in Webers like that. So that would be the magnetic flux. Now, the next part B, asks, if this magnetic field is decreasing in strength, what would be the direction of the induced current in this triangular wire here? So you have these downwards magnetic fields pointing straight down into the page, but they're decreasing in strength. So Lenz's law says the induced current is going to try to oppose that decrease. So if you have downwards pointing magnetic field vectors that are decreasing in strength, you'd want to apply a magnetic field which is also down to try to cancel out that decrease, to try to build them back up in the same direction. So I'm going to draw these red X's in here to indicate that's going to be the direction of the induced magnetic field. The B induced is going to be down into the page like that to build up these blue magnetic field vectors, which, as the problem states, are decreasing. So the question now with your right-hand rule is, if the magnetic field is down, what direction of current would cause that to happen? Well, if I put my thumb in the direction of, say, this very convenient bottom wire here and curl my fingertips around, that gives a downwards magnetic field. It's consistent over here as well, that if I put my thumb in the direction of this wire right here and curl down, also down into the page there as required. And so I'm going to conclude then that the induced current in this thing is going to be clockwise, because I think the induced current is going to be that way, and that way as it goes around to battle that decreasing flux. So my induced current here is definitely going to be counterclockwise in this particular triangle.